we go over chemical equilibrium. Well, what is chemical equilibrium? Now, this is simply a condition in the course of a reversible reaction where there is no net reaction, which is, there is no net change that is occurring in the amount of reactants and the amount of products being produced. Okay, so no net change in amount of products and reactants produced. So we need to understand something here. Well, when a chemical reaction is happening, take for example this reaction where you've been given, let me use a balanced reaction AA plus BB, and then this is giving us, okay, this is giving us, let's say, CC and DD. Well, the small letters are just representing the number of moles when you balance the chemical reaction. For example, when hydrogen reacts with oxygen to produce water. So to balance this chemical reaction, we put a 2 there, and we're going to put a 2 here. So this is what we are representing by this. Alright. Now, let's go on. So we are saying a condition in the course of a reversible reaction. So when we see arrows like this means it's a reversible reaction. It can either go forward or behind. So the reason as to why this arrow is much shorter is because this reaction is more going forward than it is going behind. Well, we have got what is called homogeneous reaction. For homogeneous reaction, it means they are in the same phase. They exist in the same homogeneous phase. For example, if all of them are gases, then that reaction is homogeneous. Heterogeneous reactions, some of them they are in different states. For example, you can have solids, liquids, and gases in the same reaction. And now, when you compute Q, which is called the reaction quotient, well, the reaction quotient is simply a ratio of the products, the concentration of the products divided by the concentrations of the reactants. So, reaction quotient. I don't know if you are able to see this well. Alright, so that is the reaction quotient. Now, let's proceed. We are saying when we calculate Q, Q is given by the concentration of the product, so C to the power C, and then D to the power D, and then divided by the concentration of the reactants, and the reactant we've got A, that should be raised to the power A, and then B raised to the power B also. So the time when this reaction reaches equilibrium, that means the point where there is no net reaction. The rate, the speed at which the products are being formed is equal to the speed at which the reactants are being formed. What we need to know is that whenever a chemical reaction is happening, as much as these are forming products, the products are also colliding to form the reactants. But there will be a point in time when the speed at which both of them are forming each other is equal. Such a point, then we've reached equilibrium. And so at the point of equilibrium, the reaction quotient becomes equal to K, which is the rate constant or equilibrium constant. And so we are saying at equilibrium, Q is equal to K. Now, when we are using concentrations, we are going to call this as Kc. Okay, that means the equilibrium constant when we are using concentrations. And so we are saying this Kc is going to be equal to the concentration of the products, that is C raised to the power C, and then D raised to the power D, divided by the concentration of the reactants, that is A raised to the power A, and then B raised to the power B, where small letters, which are superscripts, are just representing the moles, balanced moles. That is at equilibrium, where the reaction quotient is equal to the rate constant. Now, when we want to find the same reaction quotient in terms of pressures, and that is at equilibrium, then what we are going to have is the rate constant using partial pressures, when we are using the pressures or the partial pressures of the reactants and products. And so Kp becomes same, it is the pressure of the products. So we have got first the C. What is the coefficient of C? That is C. And then multiplied by the pressure of D. What's the coefficient of D? So this will be raised to the power D, that's a mole, divided by the pressures of the reactants. So the pressure of A raised to the power A, that's the coefficient, times the pressure of B raised to the power B. Now, from the universal, let me just say from the gas law, the gas law tells us that pressure times volume is equal to number of moles times universal gas constant times temperature in Kelvin. And so if we divide by the volume everything, we are going to have pressure being equal to number of moles over volume and then RT. Now we know that number of moles over volume is equal to molarity, and so pressure is actually equal to molarity, this is the temperature here, times the rate, the universal gas constant, and then times the temperature in Kelvin. And so when we are using partial pressures, we can as well substitute this equation, knowing that this is the molarity here. And so in this equation where there is pressure, we are going to substitute this equation. Okay, that means the pressure of C, as we can see, pressure is equal to that, so that is going to be equal to the molarity. This is molarity, and in this case we present molarity using this, or just concentration, because molarity, one type of concentration is molarity, which is in terms of moles over volume. So because we're talking about C, that will be the concentration of C raised to the power C, and then we have got RT. And then for the pressure, okay, what do we have again? Okay, this is, we're not going to put this power here because we're only interested in the pressure. We are just substituting molarity, not even coefficients which I'm putting there. So that will just be the concentration of C times RT. And then the pressure for D is going to be the concentration of D times RT. Then the pressure for A is going to be the concentration of A times RT. The pressure for B is going to be equal to the concentration of B times RT. So let's go on and substitute. So we are seeing that Kp is equal to, where there is Pc, we are going to substitute what we have here, and so that will be the concentration So I think that is going to be equal to the concentration of C multiplied by RT. But remember, it is raised to the power C, so everything here raised to the power C, and then where there is D, we are going to put concentration of D times RT, also raised to the power D. And then down where there is pressure of A, we are going to replace that. So that is the concentration of A times RT, and then raised to the power A. Where there is pressure of B, we are going to substitute the concentration of B multiplied by RT, also raised to the power B. Now we proceed from here. We can distribute this C to everything which is on here because it's applying to all of them. And so this is going to be equal to, well, I'm going to write concentration of C, and then RT I'll put it alone, and then this C is going to distribute to C and to RT. So that is going to be C and then C there. And then we have got the concentration of D and then RT. So that is going to be raised to the power D, and this also raised to the power D because this D is going to apply to both of these. And then also in the denominator, we have got the concentration of A raised to the power A, and then RT raised to the power A. And then we have got concentration of B raised to the power B, and then we have got RT raised to the power B. Well, at this point we can see that I can put the concentrations together. So we've got the concentration of C, and then we also have concentration of D, that is also raised to the power D. And then we have got RT raised to the power C, RT raised to the power C, I mean to the power D there. Now we can see that these are same bases and they are both on top, they are multiplying. So same bases multiplying, just add the powers, and so that is going to be to the power C plus D. And then we are going to divide that by, we have got the concentration of A, and then I'll write first the concentration of B. Concentration of A is raised to the power A, concentration of B is raised to the power B, and then we also have RT there. We can see that this and this, the same bases multiplying, we are going to add the powers, so that will be A plus B. So I can remove this space. Okay, so this is a D here, and so this will give us Kp being equal to the concentration of A of C raised to the power C, and then the concentration of D raised to the power D, divided by the concentration of A raised to the power A, the concentration of B raised to the power B. And then we have got same bases dividing. What happens to the powers? So we just do subtract the powers. So that is going to be C plus D minus A plus B. Now, what does A mean? C plus D and A plus B mean? Well, we can see that this portion here is equal to this portion here. And so where there is this portion, we are going to substitute Kc. And so we find that Kp is equal to Kc, and then we have got RT raised to the power C plus D. We can see that these are small letters. These are the moles on the product. So moles of product, and then minus A plus B. We can see these are the moles on the reactants. So that would be moles of reactants. Okay, so we can proceed and say, therefore, Kp is equal to Kc, and then RT to the power. This moles of product minus moles of reactants, we can just abbreviate it as delta N. So this gives us the relationship between Kp and Kc. The rate constant using partial pressures and the rate constant using concentrations related by this equation. Of course, we can as well just substitute where there is the universal gas constant. That is a constant. So we can as well say Kp is equal to Kc. Where there is a universal gas constant, we put 0.0821, and then there is T, and then raised to the power delta N. So this is going to give us the relationship between Kp and Kc. Alright. Now, another thing that we want to understand is when we were writing the rate constant, the equation for the rate constant for a non-homogeneous reaction, for a heterogeneous reaction, so for reactions which are heterogeneous, which are not homogeneous, for example, if you've been given A, which is a solid, plus, let's say B, this is B, which is a gas, is producing SSC, C, which is a gas, and then plus DD, which is a liquid. So when we are writing the rate constant at using concentrations, using partial pressures or anything, so let's say we want to express Kc. Kc is going to be the concentration of the products, that is C. You only get those which are in aqueous or gaseous state, don't get solids and liquids. So that will be the concentration of C to the power C divided by the concentration of B to the power B. So we'll not use A because it's a solid, do not use G because it's a liquid. You only use those which are in aqueous or in gaseous form. So that is one also important thing that we need to know. Now, we have mentioned to say when a chemical reaction is happening, we can calculate the value of Q. So this Q, when it is equal to K, we are saying this is the point of equilibrium. The rate of the forward reaction is equal to the rate of the backward reaction. Well, we are also able to have a point when Q is less than K, and when Q, this is for Q is greater than K, and when Q is less than K. Then what does that mean in this case when we have got those? And so, starting with what we have here, let's say we have got a chemical reaction, A going into B, and initially the concentration here is 2, whereas the concentration here, let's say, is just 1 on the product. And then at equilibrium, the concentrations are supposed to be the same. So this is the first one. And then at equilibrium, the concentration of A is going to be equal to the concentration of B. This is 1.5. This is also going to be 1.5. So the concentration on the reactants and on the products is the same. And then another one, when A is going into B, the concentration this side can be more than the concentration this side. Okay. So we are saying that when we calculate the value for K at equilibrium, let's assume, so K at equilibrium, if we want to calculate, remember it is concentration on the products divided by the concentration on the reactants. What value are we going to get? The value we are going to get is a 1 in this case, if these are the values. Now, because this is not at equilibrium, we cannot find K. Well, when we find K here, the same value for K we have found is the same value for Q. because when we are calculating Q, you use products divided by reactants. That is also equal to a 1. Now that we know the value for K, what of for the first one, the first condition? We can't find K because it's not at equilibrium, so we're going to calculate Q. And Q will be given by concentration on the products, that is 1, divided by the concentration on the reactants, which is 2. So we see that Q is small. Okay. And then if we consider the third one, we can't calculate K because it's not at equilibrium. We can only calculate Q. So Q will be concentration on the product, which is 2, divided by the concentration on the reactant, which is 1, and that is going to give us a 2. So we see that when the concentration is more on the product, it is less on the reactants, then what happens? Q, the value for Q, we are saying Q, we have found 2, but what of K? K is a 1. So, and this is Kc actually, because it is at concentrations. We are using concentration to find that rate constant. So when Q is greater than K, for the first condition, we are seeing that the reaction has got more of products. The concentration of the product is higher than the concentration of the reactants. Now, by the Le Chatelier's principle, when a system which is at equilibrium is supplied with a stress, that means we change any kind of thing for a system at equilibrium, whether we change concentration, temperature, or even pressure, the system is going to shift in a direction to reduce that stress which has been offered. So in this case, we can say that the concentration of the product is more. That means the products are going to be reacting to form the reactants, so that the concentration here reduces or the concentration here does increase. And so when Q is greater than K, the reaction will be, the equilibrium shifts to the, so we are saying equilibrium is going to shift left. So it will be going towards the reactants to form more reactants. Now if we consider the first condition which we have here, the value for Q is less than the value for Kc, because Kc is greater than Q. So when Q is less than Kc, what does that mean? That means we have got more on the reactants than we have on the products. So because of this, by the Le Chatelier's principle, the reaction is supposed to proceed in this direction, so that we use up more on of the reactants, we have products, so that we reach a point of equilibrium. And so when Q is less than K, equilibrium shifts to the right. Okay, so these are some things that we need to get to understand when we are talking about chemical equilibrium, and this is very important. So when we've been given a certain value for Kp, and then let me use Kc, we've been given Kc at a certain temperature, and then they've given us now some certain conditions. We want to determine the direction in which a reaction is going to proceed. Well, we need first to understand what will be the value for Q. If we calculate Q just by looking at the data that we have, concentration on the products divided by the concentration on the reactants, we are going to look at this condition. Is it that Q is greater than K, or Q is equal to K, or Q is less than K? Depending on the condition which is present, we are going to tell the direction in which the equilibrium is going to shift. Well, that is all going to be for this video. Thank you so much for watching. See you in the next video.